Hello everybody and welcome to Chapter 6, our first chapter of Unit 3. We're going to cover the structure of atoms, including quantum mechanics. So first we want to talk about the wave nature of light. And light will fall into the electromagnetic radiation spectrum. In this spectrum, we can see different types of radiation ordered in terms of their wavelength and their frequency. What's important about this spectrum is that you are able to compare the different radiations. You don't need to know their specific values of wavelength and frequency, but you should be able to qualitatively compare gamma rays and microwaves and tell me which one has a longer wavelength and which one has a higher frequency. It's also important for you to be able to do that with different colors. So violet has a smaller wavelength than red. So take a qualitative study of this, know how the radiation falls on the spectrum, and you can study this actual picture on page 213 of your book. Some common characteristics of waves: we have a wavelength, and we'll use the lambda Greek symbol for wavelength, and this is the distance between the wave peaks. It will determine the color of light, and it's measured in meters. Our frequency, which is indicated with the Greek letter nu, a fancy looking V, is the number of wavelengths per second, and that will be measured in hertz or per second, 1/2. There's a very specific relationship between wavelength and frequency. All electromagnetic radiation moves at the speed of light, so it all moves at 3.00 times 10 to the 8th meters per second. If we look at two waves, or sections of waves, you will notice an inverse relationship. In the first wave, we have a very short wavelength, but there's more waves in that segment, so it has a higher frequency. The bottom wave, or the second wave, has a very long wavelength, and there's fewer waves in that segment, so it's a low frequency. Using this inverse relationship, we can write a mathematical expression: speed of light equals the wavelength times frequency. Using this, if we know any frequency or any wavelength of light, we can figure out the other. So if we know the wavelength, we can find frequency. If we know the frequency, we can find wavelength, because the speed of light is always 3.00 times 10 to the 8th meters per second. Let's use our new expression and solve a few problems. Here, if a yellow light gives off by a sodium lamp has a wavelength of 589 nanometers, what is the frequency? So we know our wavelength. We're looking for frequency. Using our formula, we want to solve for frequency and plug in our numbers. But what's important to notice is that our units are not the same. In the speed of light, we have meters. In the wavelength, we have nanometers. So we need to take our nanometers and convert them to meters, then plug our numbers in and solve. So our frequency is 5.09 times 10 to the 14th hertz. We can do the same thing if we know frequency and we're looking for wavelength. So we know the frequency. However, in this problem, our frequency is in megahertz. We don't want megahertz, we want just regular hertz. So we need to convert to hertz, which will be times 10 to the 6th. Solve our equation for wavelength, plug our numbers in, use our calculator, and we can determine that this frequency has a 2.901 meter wavelength. So really just simple algebra here, if you know your formula. Now the wave model will not explain all aspects of light's behavior. So things like black body radiation, the photoelectric effect, or the emission spectra will not be explained by a wave model. Black body radiation involves objects absorbing all electromagnetic radiation that strike it, but they will only produce certain visible light at certain temperatures. So below 700 Kelvin, you'll see very little visible electromagnetic radiation, but above 700 Kelvin, you'll see colors like red, orange, yellow, white, and then eventually blue, which is at the highest temperature settings. This is what happens with a flame. A flame has the blue part of the flame is the hottest part. So it goes red hot, white hot, and then blue hot being the hottest. Planck's constant. Planck stated that black body radiation could be explained if the energy can be released or absorbed in certain standardized packets, which he called quanta or quantums. And based on his research, he produced a relationship between energy and the frequency. And this equation is the energy will equal Planck's constant times the frequency. And with frequency, we can plug in our speed of light over wavelength from our last equation and get another setup here. So we could also find energy by knowing our wavelength because we know the speed of light. Planck's constant is always 6.63 times 10 to the negative 34 joule seconds. Not joules per second, joule seconds. The photoelectric effect is the spontaneous emission of electrons from metal struck by light. Einstein first explained this in 1905. A photon strikes a metal atom and the energy is absorbed by an electron. If the energy is sufficient, the electron will leave its orbital, causing a current to flow through the metal. He was also able to kind of piggyback on the idea of Planck that the energy will have a relationship to the frequency of that photon. And what's interesting is that Einstein actually won his Nobel Prize for his photoelectric effect work, not his theory of relativity. It's a little tidbit of information there for you.
When an electrode in an evacuated tube, as shown here, is coated with an active metal, electrons may be emitted from the metal when it is irradiated by light. This effect is called the photoelectric effect. Einstein explained the photoelectric effect by using Planck's concept of light as a stream of photons. When light of long wavelength impinges on the electrode, no electrons are emitted. Einstein proposed that this is so because the individual photons do not have sufficient energy to dislodge an electron from the attractive forces of the metal. Even when the light intensity is increased, there is no emission of electrons and no current flows. When light of shorter wavelength strikes the surface, electrons are emitted and are drawn to the anode. Thus, a current is seen to flow. Einstein proposed that the photons of shorter wavelength light impart sufficient energy to the electrons to enable them to escape from the metal. The kinetic energy of the electrons is the excess of that which they require to escape from the metal. When the intensity of the shorter wavelength light is increased, more electrons are emitted, and the observed current increases. However, the excess energy which the electrons possess remains the same. A higher intensity of light increases the number of electrons emitted, so the current increases. However, because each photon still imparts the same energy to each electron, the kinetic energies of the electrons remain the same. When light of still shorter wavelength is employed, the electrons are emitted from the metal with higher kinetic energy. This is so because the higher energy photons have imparted more energy to the electrons, and more kinetic energy remains after they escape from the metal.
Let's do a problem. So we want to calculate the energy of one photon of yellow light, whose wavelength is 589 nanometers. Using what we know, we need to solve for our frequency. We did this problem a few samples back and found that the frequency is 5.09 times 10 to the 14th hertz. Knowing our frequency, we can use our new equation, plug in Planck's constant with the frequency, and find the energy of a photon, which is 3.37 times 10 to the negative 19th joules. If we know the energy of one photon, we can find the energy per mole of photons. And we can do that by using our Avogadro's number. So taking our energy per photon and then using our conversion that 6.02 times 10 to the 23 photons will be 1 mole of photons, we can calculate the energy of 1 mole as 2.03 times 10 to the 5th joules.